Hi everybody, this is Tom Cherryhomes with the next video in the Amiga PAC-MAN series. In the next few videos, we're actually going to be going over the concept of tasks and how tasks are going to be used in PAC-MAN to take and divide up various things that the game needs to do into asynchronous little pieces that can run independently of the main program, or rather can run while the main loop is also running to accomplish things in the background. The Amiga is a multitasking operating system, and it's a preemptive multitasking operating system, basically meaning that through its life cycle, as the operating system is multiplexing resources and allocating things and doing what it needs to do, it is scheduling lots of tasks, things that need to run so that they can have their share of the processor for a small period of time before they're preempted by another task that needs to run. The Chapter 2 of the exec manual actually gives a good overview of what tasks actually are. And the best way I can actually take and explain what they are in terms of modern computing today is they're very much like threads, but honestly a lot lighter. Because there are a lot fewer concerns that exec needs to handle. For one thing, there's no memory protection, so everything is running in the same address space. And so it literally takes and makes the design and implementation of these lightweight tasks a hell of a lot simpler. Chapter 2 actually goes over Chapter 2 of the exec manual actually goes over what tasks are, how they're scheduled by the system, talking a bit about things like task states. Each task can be currently running, that is, using the CPU. The task can be ready to run, but it isn't running by the CPU yet, or a task can be waiting, meaning it's waiting to be scheduled to be put into a list by the processor. And it goes into more information such as, okay, whether a task has been added, removed, whether the task has thrown an exception, that sort of thing. And it goes into good detail talking about how the task queues work, the concept of priority. And I will take and point out here that priority is a very good thing, especially in the context of a game, because it basically means that you can guarantee, at least as best as you possibly can, that small tasks that need to run consistently and not be interrupted can be given higher priority than other tasks that don't need as much priority here. Priority in this case is literally defined to be from the lowest being negative 128, the highest being positive 127. And you can take and change that task priority over the life of the task, either by the main program or by other tasks. It also goes into a good bit of detail here as to what a task structure actually is, and you've got all sorts of interesting little bits of data structure that you can look into. And if you want to take and write a quick little program to take and dump the tasks on a running task on a system, you can. You have access to all of these different data structures, such as where the stack pointer currently is and where the watermarks for the task are. Basically, how much stack has been used at its largest point and at its smallest point in the stack, that sort of thing. What signals are allocated, that sort of thing. It talks about task creation, and it talks about task creation in basically from its lowest level, showing you how to take and fill in the individual data structures by hand, and then using add task to basically take and add all of that in. Thankfully, there are, as well as an example program showing how to do this by hand. Thankfully, there are some convenience methods such as create task and delete task, which can do most of this work for us. It also takes and talks a little bit about stack. Now, every task needs a bit of working memory to take and do things in, and this working memory is essentially the stack. And it corresponds very well in C to your local variable storage and then some. So for this purposes of our developing our tasks here, I'm allocating roughly 1,000 bytes to the stack for these particular tasks, with the intention that as these tasks come together and we start to integrate them, we'll take and fine-tune how much stack is given to each of these tasks to maximize memory usage. Finally, it talks a bit about task termination. When a task no longer needs to be done, it can be removed. You've created the task, you can use rem task or delete task to take and remove the task. As we go later on in the video here, we'll also talk a bit about signals. And signals are basically a way that you can take that one task can signal another task to do something, such as when a message is actually passed across. Later videos will start talking about messages and using messages for communication between tasks, but this first particular task that we're going to be doing is going to be completely standalone. That is, it's literally going to be created, it's going to do its thing, and then when we're done, we're going to delete the task when the program exits. So we'll go ahead and put this up here. Needless to say, if you want a good in-depth look at what tasks actually are, Chapter 2 of the Exec Manual is a good place to look. This is essentially the program that we're going to be doing here. We'll go into our PAC-MAN folder and we have a PowerPellet task. And the whole purpose of the PowerPellet task is to basically blink the power pellets or the energizer pellets. And since power is smaller than energizer in terms of letter count, I opted to call it a PowerPellet task. It is based entirely on the draw maze test harness here. I took that in, hollowed it out, and then put in my PowerPellet code here. And this is what it looks like. It sits here, it runs, it blinks the power pellets, and it does this autonomously while other things are happening. Now, part of what we're doing here is to show the evolution, not just how to use these particular operating system routines, but the evolution of these operating system routines as well. As an example, if we take and load this same demonstration program under Kickstart 2.0, I'll take and just execute another copy here. And we will quickly boot into my Amiga 3000 here, which running Kickstart 2.0. 2.04, and we will load my PAC-MAN tests, which I've made a backup of this. Let's have a look at it. And if we go into it here, and we go into PowerPelletTask, same thing here. I'm going to take, just for a second here, we're going to put these side by side so you can see. If we take and run this here, you'll notice that in this particular version of the operating system, if I do things on intuition, intuition is actually taking and forbidding access to all the other tasks in the system for the duration of running its think task so that it can reorganize the windows and whatnot. So you see some noticeable pauses when things move around, when things get resized, that sort of thing. But if we run this same demonstration over here on the 2.0, we'll see that that no longer happens. So it's an example of how the system routines improved over time and when they improved over time. And you can see that even though this is running on a 25 megahertz machine versus a 7 megahertz machine, the durations are roughly the same. And that's because we're using the timer task to take and blink these Energizer pellets, power pellets. Okay, so how do we take and build this goofy thing? Well, let's start with that. Now that we are exactly 10 minutes in, 10 minutes and a half minutes. Let's go ahead and I will do this. I'll just do this over here. We'll start by basically taking and duplicating draw maze. And moving it out once it's done duplicating. Come on. Got lots of files here. Just give it a second. Yeah, come on. There you go. Pull this out. We'll rename it. And we'll just call it PowerPelletTask. Okay. So there we go. We go in here, we'll say that it's still called draw maze here. That's perfectly fine. And we'll start by basically taking and changing our make file real quick to change this from draw maze into PowerPelletTask. So for this, all we really have to do is search and replace. I'm building all of these as individual test harnesses, individual programs here, so that we can take and debug these things in nice, clean little modules and not have to worry so much until we actually take and bring them together. Nothing new here, just the name change. And we'll go ahead and change this guy too. PowerPelletTask. And then we go ahead and change this guy too. Okay. Now we've done all that. Now we can start taking and hollowing out and getting the pieces that we know we want to use. Okay. For anybody who wants to follow along here, the code up here, of course, is on my GitHub, so you can take a look at the finished bit. So this is a PowerPelletTask, and the only thing that this PowerPelletTask needs to do is blink the power pellets. All the usual suspects are here. We have our screen, we have our text fonts, we have our power pellets. Now, the one thing that we're going to do here is we're going to make one little change. We're going to take and do our power pellet color. And we're going to use color number 11 here, or B. And the color that we're going to use, I'm actually going to take and bring out a copy of, I'm going to take and open up a quick little deal of another WinUAE instance here. Just real quick. Because there's no, because I didn't have time to take and bring the palette tool over into 1.1. I'll just load it from my 1.3 instance. Because I can. We'll just load it from my daughter's system here. Yeah, my daughter's using the Amiga now too, and she's doing great paintings and whatnot with it in deluxe paint and just having a good time with it. Every so often we'll take and I will, since she's running an Amiga 1000 with Parsero, I take and back up the result, and I can take and run the resulting disk image over here unchanged. So now I can just take and go into tools, and boy, this tools folder needs to be cleaned up, but whatever. So I've got perfmon here, and one of the things that I have here is Pellet. And we can use Pellet to take and build our PowerPellet color. Cool, huh? So we want it to be bright, so it needs to be definitely somewhere in the upper ranges here, like the number here. FFF is white, all color bytes here. But let's pull some green back just a little bit. Well, that's already starting to look a good pink here. So what if I take and bring this back just a bit? Okay, that's FCB. That looks like a nice PowerPellet color. So that'll be the color that we take and use. Okay, FCB it is. Put that into our. We'll put that into our color table that gets loaded in via load RGB4. And of course we have maze data and all of that crazy stuff right here. I'm just going to keep this as it is. That's fine. As a matter of fact, what I'm actually going to do, I'm going to take and clean this up just a little bit. Give me just a moment. One of the things that I've done is we moved the maze data out so it can be much better, utilized here, and I'm not cluttering up the main bit of code. If we can take a look, we'll see that we have maze border, all the maze border data that's over here. I'll take and duplicate that so we can have a copy of it, and I'll bring it over. Okay. We'll bring it over. Sure, no problem. We'll just rename it. Put it back here. And if we take a good look at this, clean up a little bit. The old PowerPelletTask. PowerPelletTask. Let's just clean this up a little bit. We'll see that we have maze borders over here. And if we take a look at what's in here, all I basically did was take all the maze data and bring it out into its own file that can be included. I also took and added some guards here to take, and if it's already defined, let's not re-include it again. Common pattern here, if and def, define, and then indif all the way down here at the bottom. It also contains all the intuition border structures needed to take and draw the maze. All of this gets copied out. Now that we have this out here, I can just take and include this and not have to worry so much about the rest of it. So let's go ahead and just peel this out here. We'll go ahead and include MazeBorders.h. And we will literally take, after the color table here, we have the maze data right here. We'll make a mark set. We'll bring ourselves all the way down. And this is all of the line data needed to draw the maze. But I'm bringing it in because it allows us to take and place our power pellets in context. So we'll just go ahead, bring all this out, because we don't need it in here in the main file anymore. Almost there. All the Intuit text, and yeah, we don't need any of that shit because we're not going to be using the about box. And I will simply take and Control W that out of existence. Okay, so now that's all here, that's all gone. We still want to take and draw the maze. And of course, we have our draw border here, we draw our maze, and then we wait here for a minute. But now we're actually going to start taking and building the guts of what we need to build here. Well, we know that we want a task, and we know that we need a task for this to function. So we start basically adding in the bits and pieces that we need for our task. What is that going to be exactly? Well, we need all the exec stuff. Make sure all the exec stuff is here. Let's remove this because I want to take and really spell this out, what's actually needed here. So we need types, we need nodes because we're dealing with exec list structures here. We need lists, we need memory, which we have. We're dealing with memory allocation. Even though we're not using interrupts here, we're going to go ahead and include it here. We'll be dealing with ports later. Libraries and so on and so on. Libraries, tasks. IO. This is the equivalent of basically adding in exec.h. It includes all these bits and pieces here. We also need, because we're using a device, we need the timer device. So we can know how long to blink and how not to blink, how long not to blink. Okay, so there we go. So that gives us all the bits and pieces that we need. And fonts, maze borders, etc. We've got some structures here for intuition base, etc. And we need some additional massaging by the compiler here. Turn message port. Create port. We need to be able to make IO requests, so we need to be able to do create extended IO requests. And we need to be able to make tasks. So, create task is going to return a task structure. Bam. Okay, great. Now we've got that. Open screen, open window. And that will, now we can basically come down and start thinking about our structure, task. We'll go ahead and statically allocate a pointer to our task that we're going to create. Okay. That's the first thing that we need to do, because that's how we're going to, that's literally how we're going to deal with this. Okay. Struct task. Okay, great. Now, how do we create a task? In our case, it's pretty simple. All we really have to do when we're ready to, we call create task. And create task, as we saw above, because we made an external reference to it to say that we're going to be passed back a pointer to a task. We have our task, create task, and we give that task a name. It can be whatever you wish, but I'm kind of making it look like a file name here, and it's all easy to find, easy to remember, that sort of thing. The next thing that you have to provide is a priority. Currently, this PowerPellet task is going to run at 0 priority. It means it's going to run when no other high priority tasks are running and whenever things happen to be idle, right in the middle. So you've got priorities, recall, are either negative 127 to plus 127. So this places it right in the middle. Finally, we need to take and make a pointer to our task. This is a function pointer. It points to a void function. It just needs to go in, and it's not expected to return anything, so it should be void. So we're going to call it PowerPelletTask. Finally, create task expects one final parameter, which is our stack size. We're going to give it stack size, and if we come back up, we'll come all the way back up here. And we'll go ahead and define our stack size to be like 1,000 bytes for right now. Sound good? All right. So now that we've got that, the next thing that we need to make sure, since we're already thinking about it, since we've created that task, we want to make sure that when we exit the program for whatever reason, that we get rid of that task. Since what we're passed back is a pointer to that task, and since task is defined by nominally as null whenever it starts out, we can check if that task is defined by saying, okay, if task is not 0, since 0 is null, then we can delete task. Yeah. We just have to make sure that we do this. It's just basic house cleaning. We take and create the task. We take and come down here. We delete the task. Okay, great. So with that, now we can actually start building the bits and pieces that we know we want to do here. One thing that we do want to actually do, we need some things to actually take and blink. So we'll take and actually pull in some image data, which corresponds, it's another intuition image, just like we did with draw stage, to take and draw our power pellet just as a placeholder. This will ultimately become part of the font, but we'll just put it here for the sake of putting it here. Now, we'll take and literally draw it out here. So we need an image for our pellet. And it has a top and left relative of 0 and 0. It's 6 by 6, and it's a 4-bit plain image. The data comes from Pellet, and we're going to make sure that our plain pick is 00B so that we absolutely make sure that we select our power pellet as our power pellet color right here. I talk about plain pick and plain on and off in another video here, so I won't bring it up here. Since we have Pellet, we need to define it. And yeah, if you want to fast forward past all of this here, I'll do it, but I'm trying to do this the long way out. We've got 4-bit plain, so bit plain 2, bit plain 3. Okay, groovy, right? So we start entering in our data. One, two, three, four. So like that. And it turns out there's 16 bits of data, but those are all zeros here, so I won't put them here. So you'll see, again, 6. Okay, 1, 2, 3, 4. So that's what that power pellet looks like right there. And it's the same thing in all of the bit planes here. But because we set our plane pick here, it's only going to take and blit that into the color planes required for color B here. So we'll take and set that mark. We'll take and copy it over. And then that's our data. There's our image data for our power pellet. Ruby. So now we have our image. So now we have our image for our power pellet right here. And just to start here, we'll take and define our, we'll go ahead and, because we now have that here, our pellet here, our image data here, now we'll go ahead and make our task, our power pellet task. There's really not much to it. We'll just start, and it's going to be a blank. It's just going to be a power pellet task. And all it's going to do, at least for now, is it's going to wait forever. Wait forever. That's it. Boom. We're going to remove this for now, but for right now, at least, this task, once it's started, we don't want to take and just do, it might be tempting to do something like this and just spin, you know, or just sit and spin. But that's wasting CPU cycles because it's constantly taking and executing that code over and over and over again as fast as it possibly can, given the priority constraints. You don't want to do that. It's very wasteful. So what you really want to do at any given time, if your task is not doing something and it's waiting on something, you should use wait, or if you're dealing with message ports, waiting on a message port. But for now, we're just going to take and wait for no signals, which just means we're going to wait here forever and nothing's ever going to come. We're waiting forever for Godot. Okay, so at that point, we've got our task. It's sitting here and it's spinning. And our main task is just hammering along. It creates the task, and it's just going to sit here and do a delay 600, and nothing is going to happen, okay? We'll go ahead and just build this as it is right now and see where we're at in the grand scheme of things. You know, I'm doing on time, by the way. Yeah, 30 minutes. I guess you guys like this longer form content here, and people are asking me to take and show more of me putting in the code and whatnot. So yeah, I'm trying to oblige as best I can. The usual suspects, I take and go into system here, go into my CLI, and we'll just take and build the goofy thing. Since it's sitting out here on my T-disk, I'll just say, am I here? Trash can. Oh, I'm still on my workbench, aren't I? Yes, that's why. Excuse me. There we go. PowerPelletTask. So, there we go. We'll go ahead and just build this out. Execute, make, and see what's going on here. And point of fact, I'll take, just to prove that this task is actually running here, we'll do this a little bit differently. Go wait 0, okay, fine. I will take and do DisplayBeep null. Probably one of the most useful little debugging tools for taking and debugging tasks if you have absolutely nothing else. We'll wait for this to take and complete, and then I will take and just run the build again. But this will at least show us that the task is actually functioning and is doing what it's supposed to do. All right, groovy. We'll take and save that, pull that in here. It really is kind of nice. I mean, thinking about how the Amiga operating system was designed, it was designed all around these concepts of really fast list functions, building nodes full of connected together as linked lists, iterating through them very quickly, using them for everything from memory allocation to scheduling to everything else and everything else in between, and making something that that ran extremely fast, that could multitask, and could do so very efficiently. Just overall, it really strikes me just how much thought, even with the extreme time constraints that the Amiga development team were under to get this thing out and on the shelves, how much thoughtfulness they were able to put into even this earliest version of the operating system. And that's part of what I'm trying to show here. I'm trying to basically prove the point that Amiga gave developers a good set of tools to take and make really great applications and to make them work nicely, cleanly, and efficiently in a multitasking environment. There are always going to be situations where you have programs that need more efficient use of the hardware. That's just fine. I'm trying to basically just show another perspective entirely, something that has been very grossly underrepresented, especially in terms of game development. And I hope this is coming across. Okay, so we got this. Okay, great. Now let's take and run this goofy thing and see how we're doing. You can see right there, bam, okay, it drew the maze, it ran the task, it blinked, it's waiting for the task to complete. The delay is happening in the main thread, and once the delay is up, it'll take and close everything out, close the task, and then we're done. So we can see that this task that we've just created is now working as expected. Okay, well, let's actually start implementing it and putting some things in. Well, we do know we definitely need to put some some dots in here so we can see something that we're going to blink. So we'll go ahead and basically do that. Now, for this, all we really need to do after we do our draw border here, we just need to do some draw images to take and draw our power pellets on screen here. And I'm going to do this as quickly as humanly possible. I'm just using the draw command onto the raster port, drawing our pellet image at points on the edge of the maze where they need to go. You'll see same X, same Y. They're all being drawn on the same axes here. You know, nothing special here. But we're just part of the magic of doing your own cooking show. You've done all this before, so you can make it look like magic. Yeah. So there are our 4 power pellets. We'll take and build that. And in fact, I probably could have just added that in going ahead, but I really wanted to show that the task actually worked without anything else. We'll go ahead and make again. Yeah, my daughter surprised me just out of the blue this about 6 days ago now. She loves to buy stuff on AliExpress all the time, And that includes like arts and crafts things and shirts and different things. We've had to tell her to take and back off on it a lot because it's becoming a bit of a habit. But one of the things that she bought was this black t-shirt, this black girl's t-shirt with the original Amiga logo on it. And that really, it was a nice surprise. I was a very proud dad for that one. Yeah, you know. As always, if you enjoy this content, feel free to take and comment on things that I should cover in the future. Feel free to take and subscribe for more interesting content. We'll wait for this to finish. All right, so now this is here. Our executable is growing ever so slightly here. But we'll see. Okay, that blink is still there, but we can now see our 4 power pellets right here. And they're staying on because nothing's blinking them yet. Well, let's start making stuff. Let's start making things to blink them. Okay? So now we actually start making the last part of this video here where we're actually taking and implementing the meat of the task. Hold on. Hold on a second. DisplayBeep. Sorry, I had a frame BART there for a moment because I wanted to zero in on a very specific line without scrolling for it. Okay, so now let's actually start implementing our PowerPellet task. And that's pretty easy. What we really need to do is go ahead and define a couple of things that we know we want to take and define here. We want our blink color. Remember, we wanted our color to be F, C, and B. So that would mean F for the red, C for the green, and not bling, B for the blue component. We need this because essentially we'll be using set RGB4, which takes these parameters individually to take and change a single palette color rather than loading a whole color table in memory. Really, what we're gonna do? We need something to act as a toggle. Sure. I keep forgetting it's KNRC. So, yeah. All right. So now this task is just going to sit here and do something forever. Now, interestingly enough, if you look inside of intuition.h, there is a macro that is literally called forever that evaluates out to while 1, but it's a macro just called forever. This is an RJ Michaelism. He uses this all over Intuition and just decided, okay, fine, I'll make it public. So we're guaranteed to indicate that we have control of the screen and we know the screen is ready by the time that the task starts, so we don't have to check for it. We can just go right into calling our setRGB4 call here. setRGB4 has a handful of parameters. One of them is quite literally a pointer to the viewport for the current screen that we want to change colors for. And we want to change our blink color. What is our blink color? Recall that we wanted to change color B. So that's our blink color. So we have our viewport, the color that we want to change, and the next 3 parameters are the color parameters for that here. But we want to change it depending on the state of the be on off variable here. So we'll use a condensed conditional, ternary conditional for this. So is blink on and off true? If it is, set it to blink R. Otherwise, we set it to black, which matches the background. Again. There we go. We then take and turn around and toggle to be the opposite of what it was before. With the byte that we have here, setting it to 0, we take and set it to not be on and off. So now it's be on off. So be on off is not be on off. Flip back and forth. Bang, 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 bang. Now, the one thing that we do need to do, recall that I said that we didn't want tasks to spin. We didn't want to take and just do a, you know, we can't just do this, because you can't use DOS library functions. You can't do that. And you can't really just spin waiting for something to happen. Whatever. Yeah, you can't do that. You're just wasting CPU cycles taking and making that happen. Thankfully, we have in the operating system a timer device that we can talk to and that we can ask for it to wait. And as part of doing its I/O requests, it will, in a very operating system friendly way, cause our task to wait until the timer expires. Let's go ahead and use it, but we need to take and implement a function to do that so we don't clutter up our main little PowerPelletTask here. So we make a deal here, blink pellet wait. All right, Ruby. So void blink pellet wait. And the purpose of this function is to wait a little bit of time and then return using the timer device. Well, how do we do that? This. We start by taking and defining a handful of things that we're going to use locally. Since we're talking with an I/O device, and the I/O device wants to, and we need to be able to communicate with the I/O device, we need to create a timer port. We need to create a message port for our communications to our timer device to go over. We need to take a time request, which is essentially a message that we're going to send down that port to the timer device. And the values of how much time we need to wait, we need to take and create a structure for a time value. Now, if you've dealt with wait functions in Unix, this might look a bit familiar in a second, because it's a very similar structure to how you take and represent small bits of time inside of Unix. Fixed price, and we go ahead and make a. We keep an error device here. Okay, so the first thing we need to do, we need to create the timer. First thing we got to do, though, we have to create a message port that we can use and that we can pass to the device so that it can reply back to us. And since this port is just local to this task right here, we can pass, normally you would pass a name right here that would say, okay, this is my port. And anything else in the system could use find port to take and find this port to take and pass it back in timer port here. This is a private message port. We don't want it to show up in the list. we want to keep the list clean. If nothing else is going to use it, we create a private port. Then we check, and if timer port, we just whatever. We just return fine, whatever. We can't do anything else because we can't make any other messages. There's no point. We just bail. But we need to make a message now. We need to create a message using create extio. Create extio requires a destination timer port that we're going to be dealing with here. And since this is an extended IO request, we need to say, well, it's our IO request plus the number of bytes that are required to hold all of the parameters of the time request. So we need to pass a length in. In this case, it's the length of time request. Okay. Boom. If that timer message doesn't happen, we bail. But if it does, if it works, we can take that now and we can open a device. We can now open our device. We now have our message that we've constructed. We have our port that we're going to go to. And now we can immediately call open device. Timer name is defined in devices timer.h up above there. It resolves to that, basically. So the open device has that, and like all devices, there is a unit number that you can specify. In this case, the timer device uses the different unit numbers to determine which timer to use. You either have unit V blank, which means is a low resolution timer that works in 60th or 50th of a second. And the nice thing here is that the timer device here actually takes the differing vertical blank values, for example, 60 Hertz for NTSC, 50 Hertz for PAL, and adjusts the timing calculation so that they wind up being the same in the first place. So you got unit V blank, but you also have the other one, which I can't remember the name of right off the top of my head, which basically means use the high resolution timers in the CIA chip. We don't need that, so using that would be a tremendous waste of resources because you only have 2 CIA timers inside your Amiga in the first place, so let's just use VBlank. Again, it'll take and adjust timing as needed anyway. And we want to pass it our timer message that we just passed here, 0. There you go. We open our device, ready to go. And if error, then we figure out, okay, this is a clean way to take and clean things up a bit. Is there a reply port that's been attached? Yes. If there is, then we take and delete it. Then we take and close the device using the create extio message that we've created. Then we take and delete the message using delete extio. It deallocates what create extio did for us, and it's the same thing here. Time request. Boom, and just return. Okay. We've now taken and brought up our device. Our device is up. We can now send messages to it to do what we need to do. In this case, we need to tell it to wait for a certain amount of time. So set the timer to fire every 100,000 microseconds. Meh. Okay. All we gotta do, we have TV, which we defined up there. That's the time value structure that we have here, and it has two members. First is number of seconds that we want to wait. We don't want to, we need to wait less than 1 second, so that's 0. And we want to wait 100,000 microseconds. Again, if you're familiar with how time values in Unix are specified, this may look a bit familiar to you. The variable names may be slightly different. So we can take that now. We can fill in our timer message and say, since this is an IO device, this is the command that we want to send. We want to add a timer. And the time comes from our time val structure above there. Finally, we want to do it. Now, the interesting thing, this is where the delay happens. And while this is happening, this is very important. It's going to stay right here. Since we specified do IO and didn't do begin IO, this becomes a synchronous IO request. And so it's going to sit here and wait for the IO device to signal to our task that the IO request is complete using the signal structure that's built into exec. Okay, so there we go. Okay, it's going to wait here, and because it's waiting here and waiting in an operating system friendly fashion, we don't have to spin our wheels waiting for the request to finish and eating up our CPU time. Okay, so now we've got that. We can now tear down and close the timer. We'll do this each time. We can safely do this each time. So we'll take and tear it down. TR node, we have to tear down our reply port first of all. Timer message, TR node, IO message, and then reply port. Just like that. Then we close our device. This is very similar to what we did above when things went wrong, except this time we do the same thing here. We close our device, again using extio request that we built above, and then we delete the resulting instruction. So now that's in place. Okay, we're done. This function is now done. So now we have our task that's going to take and toggle. It's going to call blink pellet wait, which will take and bring things up. Bring up our message port, set up our timer messages, set up all the bits and pieces to talk to the timer device, wait for the timer to do its thing after we've told it what to do, tear everything down, close everything off. Okay, great. And one thing that we do need to do is we need to also, now that we've closed the device, we've deleted the extio, we need to delete our port. Again, because so we don't leak. So we don't leak. Okay. Boom. Okay, delete the XTO, delete everything off, and you'll see that everything that we did at the top here, we're doing in reverse at the bottom. So it's very symmetrical. So now that all this is actually implemented, let's take and build it and see if it works. I typed all this out all at once. There may be typos here, so if there are, we'll take and fix them as we go through the compile. In fact, I can probably hear some of you screaming at the screen going, "You made a mistake here, oh my God." And if I did, please take and comment on it down below. Because again, I'm dredging all this up. This is like practically 40-year-old knowledge that's been sitting in the back of my head for freaking ever. Not being used in a long time, and I've been refreshing myself, bringing it all back to the forefront so that I can take and make these goofy videos. And of course, yeah. Okay, told you we've got some boogs. We'll take and Control XG 164. What do we got here? Timer port. Okay, got it. Fix that one. Next one, 193. Okay. 193. Structure used as... and then reply port. Yep. Another little bug there. Again, just... undefined. Yeah, same thing. And 211. Not too bad. Okay. Let's just take a look. What do we got here? What's invalid function argument? Semicolon expectonated. Okay, what did we do here? What do we got? Set RGB4. Give me a second. Let's think. I did this right, didn't I? Hold on. Give me just a moment, guys. Okay, well, let's see. Let's just see how it fares now. Excuse me. Oh, God. Let's save it here, see how it fares, and we will build again. Yeah. Okay. Well, we're close. I just have to get... Okay, so it's a semicolon expected. Really? Interesting. Okay, give me a second here to see what in the hell is going on, and I will come back. Just a second. Oh, good God. Really? A derp. That would do it. The semicolon. Get rid of that. All right. That was silly. So, yeah, that was quite literally the situation that was causing this whole thing to mess up here. So, we'll do that. We'll save that. And let's try that again now that we're not putting any stupid characters where they don't need to be. Remember, macros in C are quite literally just a glorified search and replace with some expression parsing. Oops. Especially in these early compilers. As they always say, C will give you just enough room to hang yourself. Just enough rope to hang yourself. And muddied metaphors and aphorisms brought to you by Thomas. Oops. Okay. We'll let this complete here, and hopefully this will just be great, because it's pretty close to what I actually have up here on the GitHub. So again, if you want to see this on the GitHub and look at it in context, you can bring it up in the GitHub. So, I mean, like here, I'll just pull the little tab down, and you can see right here, here's the GitHub with the code. All nice and neat. And since it's in C, it'll gladly show you all the bits and pieces, where things are being pulled from, where the structure is being pulled from, where it's being referenced. So you can see how things look and everything else. And it's just a wonderful time that we live in now. We can take and, with all the weird things that are happening with machine learning and large language models and the like, we are getting some good things out of it. You know, you can take and go in and you can look at all this. You can see how this is all put together, and you can watch as all the bits and pieces are tested and put it together. Now, hopefully everything's right, and I didn't introduce any other bugs, so this should work. There we go. There's our blinky task, and it's just sitting there doing its thing. And there we go. Bingo! Done! There's our video. So, coming up in the very next video, we will take and make the score task, which will actually take and extend upon this quite a bit. So that you can take and do, open up a public message port so you can send commands to be able to do things like update a score from other tasks, and do so entirely within the context of the multitasking environment. So, until next time, guys, have fun.